Hi, my name is Maria Elisa, and today I'm going to present my work entitled Parameter Estimation of a Mathematical Model Using Two Distinct Breast Cancer Cell Lines Under Chemotherapy Treatment. So, according to World Health Organization, breast cancer is the most diagnosed cancer subtype in the world, with 2.3 million women diagnosed and 685,000 deaths only in 2020. The systemic treatment of non-metastatic breast cancer consists of the use of neoadjuvant, adjuvant, or combined chemotherapy, and the subtype of the disease guide the type of therapy to be administered. The disease has a histological and molecular classification, taking into account the place where it begins to develop and also the presence of hormone receptors. Among the molecular subtypes of breast cancer, the triple negative is one of them, which is characterized by the non-expression of estrogen and progesterone hormone receptors, and by the non-overexpression of the epidermal growth factor receptor 2. It is associated with a poor prognosis and has an aggressive metastatic behavior, in addition to a low 5-year survival rate and higher recurrence rates after adjuvant therapy. So the cell culture technique is one of the tools that facilitates the study of the disease dynamics and allows the discovery of new therapeutic targets. So the technique is able to reproduce the behavior of cells in a controlled environment outside the organism where they can grow and divide normally, similarly to when they are growing in vivo. So among the types of cell culture, the continuous cell line is a culture characterized by cells that have a high rate of proliferation and that have no lost their original characteristics and can be maintained in culture for a long period. So in this scenario, mathematical models can provide relevant contributions to cancer research. They can help understanding important mechanisms like tumor growth, administration of therapy protocols, and others. So here in this work, we seek to fit a mathematical model of ordinary differential equations into experimental data from two breast cancer cell lines, MCF7 and MDAMB231, both under chemotherapy treatment with paclitaxel. Through this fit, we aimed to find a set of values for the parameters that best represent the real system to be described here. So here is the mathematical model. The model considers the number of cancer cells, N, and the dose of the chemotherapeutic agent. So the normal cell population is not taken here into account as the experimental data used here does not involve a co-culture of tumor and healthy cells. So the experimental data of MDAMB231 were provided by Professor Isabel Rodrigues Silva, a researcher at the University of Brasilia, and the experimental data of the MCF7 were taken from the article made by research Marcela Carneiro, cited here in the poster as reference to, also at a researcher at University of Brasilia. So here is the model with two equations. And for the parameter estimation process, we used the LS-Canon this tool is available in MATLAB. And this system here was inserted in MATLAB along with its initial conditions and an objective function to be minimized, which in this case here was the mean squared error. So here in table 1, now the results and discussion. Here in table 1, we have the values used in the MCF7 cell line estimation process, in addition to parameter values that were estimated, R, which represents the growth rate of cancer cells, equal to 0.08, with unity as they raise it to -1. Besides that, mu, which represents the rate of treatment of cancer cells, equal to 0.5, also with unit as they raised it to -1. And here in figure 1, the black dots represent the experimental data with their respective standard deviation, while the blue line is the model solution curve. And as we can see here, we got a good fit. The same process was made by in MDAMB231 cell line. So here in table 2, we have the values used in estimation process in addition to the parameter values that were estimated. So as in the previous case, we estimated R, also the growth rate of cancer cells. Here R is equal to 0.09, also with unit as they raised it to -1. Mu represents the rate of treatment of cancer cells, here equal to 7.85. In addition, here we also estimate lambda. Here lambda represents the drug elimination rate and is given by 0.92 with the unity as they raise it to -1 as well. So here in figure 2, as in figure 1, the black dots represent the experimental data with their respective standard deviation, while the blue line is the model solution curve. As we can see, we also got a good fit. So we can see that the mu parameter obtained in the estimation was different in the two cell lines. Here in MDA in MCF7, we got 0.5 and here 7.85. This is explained by the concentration of chemotherapy present. Here for MCF7, we have 50 micromolar of paclitaxel, the key parameter here. 50 micromolar. While for the MDA-MB231, we have 0.05 micromolar. So the treatment rate in the MDA-MB231 is higher than the obtained for the MCF7. In conclusion, so it was possible to estimate some parameters of the mathematical model through experimental data, making it closer to the reality of the disease to be described. So we intend in the future to obtain new experimental data on co-culture of cancer and normal cells. Thus, we will be able to improve our model, include equations for normal cells, and parameters that represent the competition between cell populations. So I would like to thank the graduate program in biometrics at Universidade Estadual Paulista, Unesp, and CAPS for the financial support. Thank you so much.